Today, computer vision is all around us. Snapchat filters, Instagram selfie filters, diagnosing tools, autonomous vehicles, and so much more. Computer vision is used in our everyday lives. Throughout the years, computer vision has gotten better, but it wasn't until the neural network renaissance in the 2000s where we got major improvement of computer vision. It was the creation of the convolutional neural network, or CNN for short, that has revolutionized computer vision and has allowed us to have all these cool features and products that we use on a daily basis. In this video, I'll discuss what computer vision really is, how CNNs work, and how I've personally used them to address a big health problem. So without further ado, let's get into it. So, what really is computer vision? Computer vision is what it sounds like, the ability for a computer to have vision or see. What I mean by see is that computers can interpret images, videos, and other visual representations just like we can. It is first important to recognize how computers actually interpret images and videos. We interpret images and videos by the light that hits our optical nerve in our eye and makes sense of the signals in our brain. Computers work exclusively with numbers, and with images and videos, these things can be represented as numbers as well. Images are just made up of pixels. Each pixel has a value attached to it from 0 to 255. 255 means it's at a maximum intensity, and 0 means that it's at the lowest intensity it could be. In each image, there are 3 color channels, or 2D arrays of pixels which are stacked on top of each other. The color channels are red, blue, green, or RGB, and the pixel values in each channel tell you how intense that color is for that certain pixel. These pixel values are what computers use to make sense of images. This also extends to videos since a video is just a cycling sequence of images. Now we have a sense of how images and videos can be represented. Let's see how the CNN uses this to create really cool products like computer vision. So the purpose of any machine learning algorithm is to optimize these parameters in the function, and we want to do this to yield the best output, and we do this by using optimizers, which are essentially fancy calculus operations. Now CNNs add extra functionality to our neural networks by using convolutions. And to get an understanding of what happens in this special convolutional function, you need to first understand filters. A filter is just a grid of values, or in mathematical terms, a matrix of numbers. If an image is also just a grid of numbers, a filter is essentially a smaller grid that is slid across the image grid. Every time the filter is on top of the image grid, the corresponding part of the image grid is multiplied by the corresponding pixels of the filter grid. It's essentially matrix by matrix multiplication. Here's a visual representation of how this works. You can see the filters being slid across the image grid and is being multiplied, creating a new grid of values. When the filter is done going over the whole image, one convolution has been finished. Hence, why they're called convolutional neural networks. Okay, but what's the point of all this? What the filter is doing is creating a new grid of values that are the features of the image. The filter can extract different features depending on what the values of the filter's grid are. For example, this 2x2 filter recognizes horizontal lines in an image, and the output of the filter is a feature map, which shows all the horizontal lines in that image. This is the purpose of a filter, and in part the principal functionality of a CNN, to produce feature maps and extract important features of an image. And by doing this, it's much easier to do computer vision when you only have to consider the most important parts of an image and you already have all the features deduced. The values of the filter's grid are the parameters of the CNN. This is where the machine learning part comes in, where an algorithm learns to find the best values in the grid to create the best feature maps. Now this is in contrast to a classical neural network, where there are parameters that just need to be optimized, just like these CNNs. However, they differ because of the functionality of these optimizers and these parameters. And if we can optimize these parameters, we can create the best neural network to get the job done. Now, filters are what make CNNs work, yet there's one more thing that is used to ensure accuracy. Pooling is used to generalize features of an image and represent it in a compact way and bridges convolutional neural networks to classical neural networks. Now, classical neural networks need a constant size input that is information dense. Pooling layers can give these classical neural networks the information dense features of an image in a constant size. There are many different types of pooling layers with different function, but the most popular type of pooling layer is the max pooling layer. The max pooling layer takes the highest value after convolution and puts it into a new matrix. This feature extraction allows for a new matrix that is more information dense and is a constant size, that the classical neural network can have an easier time deducing an image and that becomes more accurate. And so with filters and pooling, all there's left to do is train a classical neural network to use that input from the feature maps and to just deduce the things that we want to do. And that's a very simple task that we've been able to do for a very long time. So this is what the main purpose of CNNs are, and this is essentially how they work. So I essentially took the idea of a CNN and put it to an own use to create a cancer detector. Using the methods of a convolutional neural network, I figured out if an image of a microscopic scan had cancer or not within it by using cancer cells as my test data and performed feature extraction and trained a classical neural network to predict if that image of a scan had cancer or not. Here's the code for the project, and after training the code and after training the machine learning algorithm for a pretty long time, I got to an 80% accuracy, meaning any image that you give this classical neural network, 80% of the time it'll be correct in telling you if there's cancer or not within the image. Now the CNN actually works really well, and this has a very practical use in health scenarios. And things like this are just the new and easy things that we can do with CNNs. There's a lot more going on in the future. The fact is, computer vision can be applied in so many different areas. So this is why it's instrumental to get in the field right now and to get an even deeper understanding of how CNNs work. And that has been the video. Thanks for watching.